chemical engineering. So in the previous lecture already I've discussed about various concentration like molarity, mole fraction, mass percent, weight percent. Then I have also discussed about normality, how to calculate the gram equivalent or equivalent weight. Then I have already discussed about parts per million. So in today's lecture I'll be talking about the limiting and excess reactants. So the important concept that arises here is that when we talk about the real industries or real industrial chemical process, that reactant are not always added in a in exact stoichiometric ratio or exact stoichiometric amounts. So the reason for this is to ensure complete so when we talk about this, so reactant are not always added in exact stoichiometric amount. What do you mean by these things? So let's say if a reaction AA plus BB is getting converted into CC plus DD. So here you won't be adding A moles of A, no, B moles of B, right? We don't usually add these things. Why? So this is not being added to ensure complete reaction. Right. B tells you to avoid unreacted expensive reactant. And then C will be to improve reaction rate, right? So these are some reasons that's why we don't add, in a real chemical industry, the reactants is not being added in the stoichiometric amount, right? So you will get to know why it is not being added. So now coming to the limiting reagent. Limiting reactant, sorry. Okay, when we talk about the limiting reactant, so the meaning of this limiting reactant is it gets completely consumed first in the chemical reaction, right? It gets so it limits the amount of product form also. Okay, so in simple word, let's say how to find the limiting reagents, right? Let's try to understand one thing. So if you have a reactant and reaction like N2 plus 3H2 which is getting converted into 2NH3, so first of all you need to balance the reaction, right? And if in the problem it is being told that 4 moles of N2 and 8 moles of hydrogen is being introduced reactor as feed, then how will you find the limiting reagent? So here you have seen that there is a reaction that is like N2 plus 3H2, which is getting converted into 2NH3. So what you have to think here, so number of moles of nitrogen is 4 here, number of moles of hydrogen is being given to you in the problem is 8. Now you divide these things with the stoichiometric coefficient 1 divided by 3. So this is your stoichiometric coefficient. So once you divide with the stoichiometric coefficient, the value you are getting here is 4, and here you will be getting 2.66. Alright. So now from here you can find out that 2.66 is less than 4. So the amount that you are getting for, let's say you are getting only 2.66 for hydrogen. So here your hydrogen will work as your limiting reagent. Is that clear? So hydrogen will be working as a limiting agent, and then nitrogen will be excess reagent. So nitrogen will remain as it is in the reaction once it is being consumed, right? So now you have to solve how much amount of excess reagent or how much amount excess reagents are there, something like that. Okay, so let's see. So 1 mole of nitrogen is reacting with, here you can see 1 mole of nitrogen reacts with 3 moles of hydrogen, or you can say that because 3 moles of hydrogen reacts with 1 mole of nitrogen. So 1 mole of hydrogen will react with 1 by 3 moles of nitrogen. So how much 8 moles of hydrogen was supplied. So 8 moles of hydrogen will react with 8 by 3, that is equals to 2.66 moles of nitrogen. So that much amount of nitrogen will get reacted, right? So you have total number of moles, of N2 supplied was 4. N2 reacted, number of moles of nitrogen reacted is your, let's say, 2.66. So excess nitrogen supplied that is how much, 4 minus 2.66, right? So I think you will be getting 1.33. So percentage excess nitrogen, how much, 1.33 by initial number of moles into 100, so 25. So it will be 1.33 into 25%. So that much percentage excess of nitrogen is being supplied during the reaction. So basically what you can see here, that percentage excess formula, percentage, that is equals to excess amount that we have calculated divided by theoretically required amount and then you have to multiply it with 100. So this will give you the percentage excess of any particular reactant that is being there in the reaction, or that is being reacting in the reaction. Now coming to the how to calculate the conversion. The formula for percent conversion is, that is equals to moles of the feed reacted divided by moles of the feed supplied and then you have to multiply with 100. So whenever we calculate the percentage conversion will be calculated based on the excess reagent, right? Because limiting reagent will get 100% consumed in the reaction. That's why for percentage conversion for limiting reagent it will be 100%, right? Okay, so let's try to calculate and I'll write in the note percentage percentage conversion, no. Right, so let's try to understand. So let's say you have a reactor for ammonia production, let's say, and the reaction which is occurring here is N2 plus 3H2, which is getting converted to NH3. So you will be supplying here your nitrogen and hydrogen. So I am telling you nitrogen is, let's say, 4 moles and hydrogen is, let's say, uh, 12 moles, and then we have to calculate what is the percentage conversion, right? So here what you see that if it is nitrogen plus 3 hydrogen, so we have to calculate 2 NH3. So first we need to understand which is limiting reagent. So this is your 4 moles, 12 moles. So what I have told you, will divide by stoichiometry, 4 moles and this is 3 moles. So you'll have to divide by stoichiometric coefficient, and this will be 1 and this is 4. So this is 1 and this is your 0.25. So your hydrogen will work as a limiting reagent, right? Because this is less. So hydrogen will get completely consumed in the reaction. So you have to calculate the percentage conversion based on the excess reagent, right? So now how much percentage conversions of excess reagent should be there? Just try to understand. So in this particular problem, what we have seen that 4 moles of nitrogen is being supplied and 12 moles of hydrogen is being supplied, but hydrogen will get completely consumed, but nitrogen will remain, a part of nitrogen will get reacted and some part of nitrogen will remain as it is. So in the problem you can see that 3 moles of hydrogen require 1 mole of nitrogen. So 1 mole of hydrogen will require how much? 1 by 3 moles of nitrogen. So how much hydrogen is being supplied here? So 12. So 12 moles of hydrogen will require 12 by 3 in so 1 by 3 into 12 moles of nitrogen. So here you can see that 4 moles of nitrogen. So now here 4 moles of nitrogen will also get reacted. Okay, so how much percentage conversion would be there? Percentage will be what? 4 minus 4 divided by 4 into 100. So that will be 0%. Why? Because if in this problem you will see that what is the ratio? A stoichiometric ratio is 1:3 for nitrogen by hydrogen, that is equals to what? 1 by 3. And feed ratio for nitrogen by hydrogen, that was also 4 by 12, that is 1 by 3. So stoichiometric ratio is matching with this feed ratio, that's why percentage convert, no one will be access. So in this problem what you will see, no one will be access or limiting reactant, right? So there will be a case where your feed will contain your feed will contain exactly in the exact ratio of the stoichiometry. So in that particular problem you will see there is no limiting reagent or excess reactant. So it's very important to understand these things. Now coming to the next part, that is the yield and selectivity. So when we define percent yield, that can very frequently get used to ask GATE and BARC exam. They basically ask these kind of questions. So percentage yield can be defined as moles of reactant converted into desired product. Moles of converted into desired product divided by total moles of reactant converted and then you have to multiply this with 100 because you are dealing with the percent. So why we are calculating this yield, I'll tell you these things later on. Then I'll talk about the plant yield, right? So percent yield sometimes also known as your reactor yield. So if reactor yield is being mentioned in the problem, just don't get confused. That's why I'm writing all of these things. Now next you can define there is a plant yield also. This is also called as the overall yield. Right, so that can be defined as the moles of reactant converted into desired product divided by total moles of reactant feed to the process multiplied with 100. So these are the two formula for yield. That is very important. I'll explain it to you with the help of some examples, so you'll get to know. So first I have described about the percent yield, that is moles of reactant converted into desired product by total moles of reactant converted, right? And then there is a plant yield, that is moles of reactant converted into desired product by total moles of reactant feed to the process, right? So let's try to understand. So you have a reaction, let's say 2A plus 3B, sorry, let's say A is getting converted into product B and product C, right? And this reaction is happening in a, let's say, reactor, right? So here at the inlet you will be feeding A, let's say you are feeding 100 moles of A, and at the reactor exit what you will get, you will be getting unconverted A, then there will be B, and then there will be C. If I am assuming B is your desired product and C is your right, and I am assuming this this is just 2B, right? 2B. Okay. Great. So if 100 moles of A is being supplied, so let's say I am assuming here the number of moles of B at the reactor exit is, let's say, 30, and number of moles of C at the reactor exit is, let's say, 10, right? So first we have to understand 1 mole of A is producing 2 mole of B and 1 mole of C. So how many moles of A got converted into B and C? So we have to understand that thing. So here we can say that 2 moles of B is being produced by 1 moles of A. So 1 moles of B is being produced by half moles of A. So here we are producing approximately 30 moles of B will get produced by half into 30 moles of A. So that is your 15. So here your 15 moles of A is getting converted for B. Now if I am talking about for C, 1 moles of C is being produced by 1 mole of A. So 10 moles of C is being produced by 10 mole of C. So how many moles of A? That will be is 10 moles of A. So 10 moles of A will required here. 15 moles of A will required here. So total how much? Total 25 moles of A got converted. So what is percentage conversion of A? That is how many moles of A got converted is 25. Initially how much feed was there? 100 into 100%. So it will be approximately 25% conversion is there. Now we are going to calculate what is percentage yield. So in percentage yield the formula is moles of reactant converted into desired product. So our desired product is B, and for conversion of B, how many moles of A was required? That is 15. So I'll put that is moles of A converted to B divided by the formula is total moles of reactant converted. So total moles of A converted into 100%. So now you must be knowing these things. How many moles of A converted to make B? That is your 15 moles. And total moles of A converted was 15 plus 10. It is 25 into 100. So percentage yield is 60%. And this percentage yield your reactor yield. This concept will come in the later section of this process calculation topic, when I will be talking about the reactor bypass and purge also. Now if I want to calculate percentage yield or percentage plant yield, right? That will be how much? Moles of reactant converted into desired product, that is again your 15 divided by what? Total moles of reactant feed to the reactor. So total moles of reactant feed to the reactor was your 100 into your 100%. It will get cancelled. So you are getting answer as a 15%. So from this particular problem we have seen that how you can convert the reactor yield or percentage yield, and how you can calculate the plant yield or overall yield. So I'll suggest you keep both of these yield into your mind, so that whenever the question comes on this particular problem, you should not get confused. It's a very important concept. Rarely you will see in any YouTube video lecture or in any class all of these things is being discussed. But I have designed this course to teach you all the fundamentals of the process calculation and stoichiometry that is involved in this particular syllabus, so that if any simple or a small concept is coming in your examination, you will be able to solve every question. Okay, I hope all of this concept is being cleared in subsequent lecture, and I would like to request you all to subscribe my channel and also share with your colleague, so that it will motivate me a lot to make more and more video for all the topics in this particular subject. Okay, so in the next topic or in the next class I'll be talking about percentage selectivity, and we'll talk about extent of reactions, and that will be the last class of this fundamentals of stoichiometry that I have started. And then I'll move towards some ideal gas and the gas mixtures behavior, right? That is also very, very important. So slowly in subsequent lecture we will be going to the toughest level of this particular courses. Okay, thank you, stay tuned.